So let us now talk about the fun side of quadratic programming, and that's applications. And actually, first we will cover the applications of quadratic programming to solve function fitting problems. So you are very well familiar with what fitting means. We are given a set of measurements, and we would like to find a function which minimizes the sum of squares between the measurements, which are called yi. So I here is the index of the measurement, y is the value of the measurement, and y hat is the estimate of the measurements, which is provided by some approximation function. So the function that we would like to approximate this data with is, in this particular case, given as a third order polynomial. So we have the x here are the x coordinates of the measurement. So for instance, this could be temperature, and that could be, for instance, pressure. Okay? So we are given a pairs of these pressure and temperature measurements, and we would like to find out the dependence of the temperature on the pressure. So x here is the dependent variable. I, again, is the index of the data point that we are considering. And a0, a1, a2, and a3 are the coefficients of the polynomial function that we would like to find, such that we minimize this sum of squares between the approximation and the actual measurement. And what we can see here is, maybe not immediately, but it certainly is written like that here, is that essentially we have a quadratic programming problem with equality constraints. Okay? Because we have a quadratic objective function and we have the equality constraint. The optimization variables, and that's very important here, the optimization variables are the a coefficients, a0 up to a3. Therefore, what is the type of this equality constraint? Is that constraint linear in those optimization variables or not? Because we have cubed, we have square here, and we are all scared when we see these kind of things in the constraints, because they kind of imply that the constraint is not linear. But what is important to realize here is that this axis here, these are known data points, so they are just constants. Okay? So the constraint is linear in those multipliers. Okay? So that's why this problem is a standard quadratic programming problem. And actually, it has equality constraints, but it is equally possible to eliminate these equality constraints using substitutions. So instead of y I hat, we could just equivalently write this formula there. Okay? And then we would immediately obtain a quadratic program without equality constraints, and we know that to solve these kind of problems, it's very easy. Actually, these kind of fitting problems, I mean, they very frequently occur in practice. So there is one kind of general way how to formulate and solve these problems. And the general way is based on writing a matrix representation of the fitting problem. So essentially what we do here is that we aggregate the vector of estimates. These are the function values produced by the fitting function. Here we have the unknown coefficients that we would like to find, and we just rewrite all these equality constraints into this form, so we just put in the corresponding multipliers. Yet again, I remind you that these x's here, these are just data points. This index here, it means it's the first data point, the second one, the third one, and so on. Okay? These functions here, they are often called the basis functions of the fitting function. So we are looking at some linear combination of those basic functions such that we obtain the best possible fit. And in the same way that we have aggregated the vector of estimates, all estimates into one vector, we can equally aggregate the vector of measurements into one large vector. And then we can equivalently rewrite the cost function that we want to minimize into this form. Okay? So this m times a, this is the matrix m, this is the vector a. That's the estimate. So this is the estimate minus measurements, and we have transpose times the same thing, which means it's the sum of squares of the differences between the estimate and the real measurement. And now we can solve this problem. So we would like to minimize that objective function. Actually, without any quality constraints, we have eliminated the quality constraints by using direct substitution into the cost function. And now we would like to formulate and solve this problem as a quadratic program, which means step one, and this is actually quite important, we have to know how to translate the problem into the standard form. The standard form has 1/2 in front of the quadratic term. It has a linear term, and it has also some constant term. So now we have to know how to relate the data of the fitting problem with the data of the quadratic programming problem. Because this matrix M, we will assemble that. That's just a constant matrix. Vector Y, we also do know. The vector A is our optimization variable. So what would be P, Q, and R in this problem such that we can solve the fitting problem using QuadProc? Can you tell me? So what would be the expansion of the original cost function? Let's transpose and multiply the brackets. What do we obtain? So that's A transpose, well, let's do it step by step. So first we transpose the bracket. So the transposition of the bracket is A transposed, M transposed plus Y transposed times MA plus Y, right? So what is that? So we have this term here, so A transposed, M transposed, MA plus
Y plus, and there are minus signs.
There should, yeah, thank you. Minus, minus. Okay. Then we have Y transposed MA, and we actually have it 2 times. So that's minus 2 times Y transposed MA. And we have Y transpose times Y. Okay. Now what we are saying is that our optimization variable will be called X. So we will just replace A by X. So that's X transposed M transposed MX minus 2Y transposed MX plus Y transposed Y. And now we have to make a relation to this problem. Okay. So what is P?
P 2 times M transpose.
Right? What is Q? Okay. Notice that we already have it like in this form. Okay, so Q transpose this is this one, but we are not asking for what Q transpose is, but what Q is. Therefore, we have to transpose this whole term. So Q is just minus 2 times, and this transpose this M transposed Y. Okay? And R trivially is just Y transposed Y. So that's what we do. And then we can actually solve the problem using QuadProc. The point here is that if you do forget to multiply these numbers by 2, you might get a completely different solution because your cost function will be different. Okay? So that's why it is important to know how to translate the original problem into the standard form. Okay? But the bottom line is we can easily solve that. I mean, it's an unconstrained optimization problem. Actually, calling QuadProc is an overkill here, because there is much simpler way how to solve the fitting problem. What is that simpler way? Give me the optimal solution here. we have an unconstrained minimization of a quadratic function. How do we solve the problem? We just make the derivative, well, the gradient of the objective function with respect to a, and we set it to 0. So what's the gradient? So that's 2m times a, and here we have to transpose, so that's minus 2m transposed y. Here that's just a constant, so that should be equal to 0. Okay, so we have 2m transposed ma is equal to 2m transposed y, and here we have, well, we can divide by 2, and we can make an inverse of this matrix here. And we have the solution. Okay? So actually we can find the solution to the fitting problem analytically. We don't require a solver for that. However, what we do require a solver for is that if we want to perform the fitting with respect to constraints. So let's imagine that again this is, say, a normalized temperature, say this is a normalized concentration. We would like to find the fitting function such that the value of the fit is always above this line here. Okay? So clearly if we don't consider the constraints, and let's say we approximate it by a polynomial of the third order, that's how the fitting function would look like as a solution to that unconstrained optimization problem. However, since we know how to reformulate fitting as a quadratic program, and because we know that in a quadratic program we can also include constraints, we can find a fit which minimizes the residuals between the estimates and the real measurements and respects point-wise constraints on the value of the fit. By point-wise constraints, what we mean is that we only have a guarantee that this new fit is above the constraint for particular sampling points, not everywhere. What I mean by that is that we could have a situation like this, that say these are the samples, and let's say that this is the boundary that we want to be respected. What we can only have is that we respect the boundary at these points of the fit, but in between the fit can do something like this. Okay? And so this point here is not part of our data set, therefore here we cannot enforce the constraint to be valid. But if your points are, I mean, if you have sufficiently many points, then you get a nice behavior. Okay? So how do we obtain such a constraint fit is, well, rather easy, because we know that we can add equality and inequality constraints. Actually, the constraints that we want to add are that the estimate, meaning m times a, satisfies constraints. So we would have z as the estimate, sorry, that should be a here, and we just want to have the estimate to respect some lower bound. And then we just convert this constraint into the following standard form, meaning we have to convert it to less equal something that means a would be equal to minus m and b would be equal to the constraints that we want to respect. So the bottom line is all fitting problems can be formulated as quadratic programming problems regardless of the choice of the basis functions, because the multipliers that we are searching for, they enter those fits in a linear fashion. So you can have non-linear fitting, like a polynomial fitting, and still solve it as a convex optimization problems, because we still have linear constraints and we have quadratic objective function. Okay? So that's constraint fitting. And let us actually conclude today's marathon by something which is called sparse fitting. So let me again give you an example. Let us consider the fitting problem of this data, and as we can see, we can obtain quite a good fit if we consider polynomial of degree 6. However, this polynomial is rather complex. I mean, it has 7 terms. And sometimes what we would like to have is maybe a worse fit, which is simpler in the sense that it contains fewer of these terms here. For instance, the green fit here, it's a little bit worse, but it is much simpler. Instead of 7 terms, we only have three non-zero terms here. And this is what we mean by sparse fitting. Sparse in Slovak means riedke. So we are looking for a fit which is sparse, has few non-zero multipliers. Like here we only have 3 non-zero multipliers, the rest are zeros. Okay? And the way how we find these sparse fits is that we still optimize all of these parameters. So they would be replaced by a's that we are optimizing. But moreover, we do require or we do want to get a solution which has a high number of those optimal variables being equal to 0. And actually, the approach how to achieve that is to that besides the fitting error that we are minimizing here, we also minimize the one norm of the vector of multipliers that we are optimizing. And we are multiplying it by some constant gamma, and this constant gamma, if its value is large, it tells the optimization to focus on a very sparse solution. If gamma is small, it tells the optimization to rather focus on a good fit. Essentially, what it would mean here in this example, if this gamma would be very large, we are looking for a fit which has as many of these multipliers 0 as possible. Essentially, the least number of non-zero coefficients is obtained where all coefficients are equal to 0. But then what would be the fit? The fit would just be a 0 function, right? So it would just be this axis. It's quite a bad fit, right? But it has very large number of 0 elements. So it's really like a compromise between simplicity of the fitting function and goodness of the fitting function. How well does it approximate the data? And we have this tuning parameter, this gamma, which tells the optimization what is more preferable, whether we rather want a good fit or whether we want to have a simple fitting function. The only problem is how to formulate and solve this problem. I mean, first of all, have you already seen this expression here, the one norm? So norms are functions which represent the distance of a point from some other point. So if we have something like this, the norm of z, then if this is the point z, which is given by z1 and z2 coordinates, then the norm is the distance of this point from the origin. The origin has 0 coordinates. And actually, we can consider different type of distances. The natural one, that's the Euclidean distance. It's this one. So it's the Euclidean norm. It's denoted by 2 here, and it's the square root of z transpose times z. Okay? That's just the Pythagorean theorem. We could also consider other distances. Didn't we cover this before? Manhattan norm, didn't I mention it in previous lectures? Okay, it was in the MPC class. Good. Okay. Now imagine you are in New York. Not just in New York, you are in Manhattan, and you know how Manhattan is laid out. Okay, it's a grid of streets like this. Okay. Now, imagine you are here. You would like to get there. What's your distance? It's not, and you are driving a taxi. Therefore, this norm is also the one norm is also sometimes called the taxi cab norm. You are taking a taxi from here. Let's say this is the origin, and that's your point you would like to get to. What's the distance you would travel? It's not the Euclidean distance because we don't have a helicopter, but it's this distance here. Okay? And that's precisely what the one norm is about also in mathematical terms. By the way, this point can as well as be like in the negative relation to the origin. It can be, for instance, here. Okay, so we would need to go here and there. A distance like this is called the one norm, and it's defined as the sum of the absolute values of individual coordinates. Okay? So this point has coordinates z1 and z2. Okay? So we are taking this absolute value plus this absolute value.
But in sparse fitting, it does not make the coefficient 0. It just minimizes their value.
I completely agree. So I should say this does not guarantee that we will find the least complex solution. Actually, we will see in subsequent lectures that, okay, what we really would like to do is to minimize the number of non-zero elements of Z. That's called the zero norm. The zero norm is the number of non-zero elements of a vector. The problem with minimizing the zero norm or the number of non-zero elements is, this is one of the most difficult problems in the world. Minimizing the one norm is one of the easiest problems in the world, and it gives a very good approximation of that difficult problem. It does not guarantee it's as simple as we would obtain by solving the difficult problem, but it will at least be something similar at much lower expenses. That's what this one norm is about. Okay? So the one norm is just the sum of absolute values. So here it would be, in case of a two-dimensional vector, it would be just z1 plus z2. Clearly, we have to consider the absolute value because distance is always non-negative. And even though we are moving in the negative direction, we are still traveling. Okay? Clearly. So this one norm, yes, it is just an approximation of the number of non-zero elements, but it's quite a good approximation. So by minimizing the one norm, it kind of gives something which is similar to the minimization of the number of non-zero elements, but it is not the same. I do agree with that. It's not the same. But it's a good approximation. And actually, yeah, so this is the graph. And actually, from the graph, we can see why, intuitively, it would kind of indirectly minimize the number of non-zero elements. What we have here in the objective function is a square function, which is like this. And the square function, what it does to small numbers, it makes them even smaller. Okay, so if the number is below 1, the square makes it even smaller number than it was originally. The one norm, on the other hand, is quite selective. The optimum is at 0, and any non-zero value will be penalized kind of equally. That's what makes a difference between the one norm and the square of the two norm. Okay? That the square of the two norm is rather insensitive to these numbers. So if the numbers are, say, between minus 0.1 and 0.1, after you square the number, for any number in the interval, you basically obtain a 0, okay, or something really close to a 0. However, with the one norm, each non-zero value would be penalized, and that's why the solutions tend to give large number of zero elements. So what we are looking here at is an instance of a problem of this form, and this is kind of the histogram which says how many of those A coefficients have corresponding values. So what we can see here is that by minimizing the one norm, a large portion of those coefficients are 0. And there is the other portion, they are this big. However, if we would instead minimize the two norm of A, this is what would happen. We would have large number of coefficients would have small values. because for the optimization, after you square the small number, they are equally good or equally bad, okay? So here, the number of non-zero elements would be much lower. And moreover, notice that here, the axis here is 10 and here is 40. Okay? So with the 2 norm, the histogram is much more spread around 0. With 1 norm, it's much more concentrated in 1. And the point here is that minimizing the 1 norm is an easy problem. Minimizing the number of non-zero elements would be a difficult problem. So let me finish by showing how do we actually transform this problem into quadratic programming. The trouble is, this is not a quadratic program. Why? Because the quadratic program would need to have a quadratic cost function. This function is not quadratic. Essentially, in one-dimensional space, it's just an absolute value. So it is not directly compatible with the quadratic programming framework. However, there is one trick that you need to remember really well because it occurs frequently. Essentially, let us look at the one-dimensional case first. So we have x as the optimization variable. It's just a scalar. And we would like to minimize the absolute value of x. What kind of problems is this? We have so far covered linear programming and quadratic programming. Is it a quadratic programming problem? We don't have any constraints. Is it a quadratic programming problem? Do we have a quadratic cost function? No. Is it a linear programming problem? Do we have a linear cost function?
More or less.
Is absolute value a linear function? Is this a linear function? This is a linear function. This is not a linear function. Okay? So this is not even a linear programming immediately. However, using one standard trig, it can be written as linear programming. And the trig is that if we want to minimize any function like this, we can seemingly make our life harder by solving this problem instead. Minimize epsilon subject to epsilon being above the function. So what we are saying is minimize the upper bound of the function. And it gives us the same solution as minimizing the function directly. Why do I say we make our life harder? Because now, here, the optimization variable was x. Now, x is still the optimization variable, but also epsilon is the optimization variable. So we have introduced a new optimization variable. Everybody should ask why. Why should I make the problem more complex than it was before? Well, the answer is that using this additional variable allows us to solve some of the problems easier. Okay? So essentially, if now f of x would be the absolute value, what we would obtain is minimize epsilon subject to epsilon is larger than the absolute value. Now, is this a linear programming problem? Do we have a linear objective function? Optimization variables are epsilon and x. Is this a linear function of epsilon and x? What is a linear function? a1 times epsilon plus a2 times x. Is the function in this form? It is. a2 is equal to 0, a1 is equal to 1. We have a linear function, so we are on a good way towards linear programming. But linear programming needs to have linear constraints. Are the constraints linear? Not really. This is a not linear function. However, when is epsilon larger than absolute value of x? We can actually write this constraint as two constraints. Epsilon is larger than epsilon x if and only if epsilon is larger than x and epsilon is larger than minus x. Do you agree with this? So we come here and we rewrite the problem into minimize epsilon subject to epsilon larger than x, epsilon larger than minus x. Voila, what we have is a linear program. So what we start, sorry? Sorry?
Larger than x and at the same
larger than minus x.
Larger than minus.
So let's say x is 5. Let's say we want to write epsilon is larger than absolute value of x. Does it hold that epsilon is larger than 5 and epsilon is larger than minus 5? If epsilon satisfies these two constraints, would it also satisfy this constraint? Yes. If x is minus 5, okay, we know that this constraint really means epsilon is larger than 5. Okay? So here it would mean epsilon is larger than minus 5 because that's our x, and epsilon is larger than plus 5 because that's kind of minus x from here. So this still forces epsilon to be larger than absolute value of x. So it's a trick, rather straightforward trick, which allows us to rewrite a problem which originally was not a linear program into a linear program. And then all we need to do, I mean, that's an alternative representation. Oops. All we need to do is to essentially introduce this epsilon variable for the one norm, include it into the quadratic optimization problem. By that, we still keep quadratic optimization, the quadratic objective function. And then we need to add these constraints into our optimization problem. And we keep linearity of the constraints. We have still a quadratic optimization function, which is strictly convex. Therefore, we can solve it as quadratic programming problem with inequality constraints. And to solve those kind of problems, we either employ active set method or some other method. Basically, you call quadprog or some other solver, and we obtain a fitting function which is sparse, meaning it contains a low number of non-zero elements. And I believe you will have an exercise in which you will practice essentially this translation process, and you will also see how the value of gamma influences the quality of the fit with respect to simplicity of the fitting function. Okay. So I guess with this we can wrap up today's lecture and see you next week.